It's great to be here and celebrate the breakthrough prizes. So I was asked to, as all were the other presenters were as well, to speak to a general audience, or at least an audience of first-year graduate students. So, so I'm a little embarrassed perhaps that my slides will be at a very elementary level, but I hope we'll have a good time nonetheless. So let's get started. So I'm going to try to explain to you a kind of arc of history, and then also predict the future, or at least predict some sort of near future. So the talk won't have a lot of specific mathematics in it, but I hope I'll tell you a story that will help orient you towards what's happening in an exciting direction of math. Okay, so I'd like to start that history in the very beginning, and I'd like to ask you to sort of do a thought experiment to start, which is to try to think of a good definition of a point. And if you come up with a good definition of a point, while I'm still talking, come up with a good definition of a line. Okay, so that's a kind of a first challenge for the audience. Try to think of a good definition of a point or a line. So there are lots of different things you might come up with, but you might be inspired by Euclid. I don't actually know whether I should credit or blame Euclid here, so it seems like there's a lot of debate about what in the Elements is actually Euclid, or at least contemporaries of Euclid, and what is later. But in any case, Euclid tells you that a point is that which has no part, and a line is breadthless length, and so you can imagine then what a plane is and what three space. Anyway, so you just keep, saying what it's not. So one of the amazing things, so I'm going to try to explain two parallel subjects that have different answers, but parallel answers to this question, and how those subjects have developed and influenced each other. And one of the recent exciting directions that we'll get to by the end is the answer in one of the subjects to what is a plane. Okay, so if I sort of lose you along the way, we'll get to a slide towards the end, where the question will be raised, what is a plane? And of course, if you're a geometer, there's probably a clear answer. But if you're a number theorist, there's not necessarily a clear answer. And, well, we'll talk about what proposals are in the future. Okay, so I'd like to start by trying to be a bit more of a mathematician and formulate this more precisely. So rather than asking what is a point or what is a line, it makes more sense to ask what are functions on a point. Okay, or what are functions on a line? Because we know properties that we want functions to have. We want to be able to add functions. We want to be able to multiply functions, and so on. So functions form some kind of mathematical object, like a field or a ring. And so all you need to do now to answer this kind of a question is you need to pick your favorite ring or your favorite field, and then propose that as the answer to the question. Okay, so all right, so what do you do? If you're in geometry, you have many, of course, the choices I'm going to force on you, don't feel obligated to live in any of the columns that I present. You can answer this in many, many different ways, and people have many different answers. But in any case, I'm going to insist that if you're a geometer, that the answers to these questions are that functions on a point are just the complex numbers. Okay, so you just assign a number to a point. And if you ask what are functions on a line, well, there are many different answers, but for the sake of this talk, let's agree that functions on a line are complex polynomials. Okay, so you might have asked for holomorphic functions or maybe smooth functions. In any case, for the sake of this talk, let's think of functions on a line as complex polynomials. So I should say Lauren credited the internet with one of her pictures. I should just unilaterally credit the internet with all of my pictures. So all of them were recently stolen off Wikipedia and various other sources. So there's I didn't have any kind of great artistic intention with this picture of the complex line, except that this was easily pilfered. Okay, so there's the complex line. It's two real coordinates. And the way, of course, that you think of a complex polynomial as a function on the complex line is given any point in the complex line, you just evaluate the complex polynomial at that point, and you get a function on that point. Okay, so it's these kind of answers are compatible. Okay, so now let's move to number theory, and you can ask the same questions. And again, let me just sort of apologize to the experts. I'm going to try to tell you. I'm going to try to insist that you play a game where these are the answers, but there are many other answers one could propose. But in any case, let's take these as answers. So functions on a point are going to be the finite field of p elements. So we take the integers and we do modular arithmetic. So we draw a clock, and every time we come back around to p, we're back at 0 o'clock. And that's just going to be our answer to the question, what are functions on a point? Okay, so we don't necessarily know what a point is, but we know what functions on it are. And functions on a line, maybe it's a little less evident an answer, but we're going to take the integers, which is the standard answer in one starting point for number theory, So the integers are the kind of analog of polynomials, and now you can ask the obvious question, which is how do you evaluate an integer at a point of the line? And well, you take the integer modulo p. So if you have an integer and you have a prime p, then you can ask what's the value of that function at the prime p, and the answer is you just take it modulo p, and you get a function on the point. So I went to the internet to try to find a picture of, this is what mathematicians might call spec z, and I went to the internet to find a picture. Maybe I should have gone to your book. In any case, I found this picture, which I found intriguing in its own right. So this is what's called the Ulam spiral. Have people seen this picture before? Okay, I hadn't seen this picture before. So what's happening here, this is nothing to do with the rest of the talk, but I'm just going to sort of tell you about the spiral for a minute. So, so what's happening here is someone's plotted the integers starting with 1. So I guess let's see if I can use this to, well, anyway, you can see one should be in the middle there, and then gone around and just erased all the integers that aren't primes, okay, and plotted what remains. And one thing that one would see, and you can see as well if you go to, say, Wikipedia, and you just Google this, you will find big pictures, so a big scatter plot of this picture, and there are beautiful patterns where primes live along diagonals more than you would expect, which I think is still some sort of open questions about when quadratic functions take prime values. What's that? Oh, I think it's just going around, like you started at 1, then you went to 2, 3, 4, 5, 6, 7, and then you've reached a new point, so you can go 8, 9, 10. I mean, I think it's just going around like on the corners of a graph. Yeah, you turned at 5 because you got beyond 1, yeah. This has nothing to do with the rest of my talk. I just kind of enjoy this picture. And I found this great quote. So giving a talk, you find this great quote, which is that, so I learned that Ulam doodled this in 1963, and he said he doodled it when he was in a very long and very boring presentation of a paper. So somehow he discovered this. But Wikipedia also told me that Arthur C. Clarke, the science fiction writer, had discovered this like 7 years earlier. So it appears in a novel of Arthur C. Clarke. I don't know what it was about. I didn't go so far as to do the research about, but anyway, maybe some alien life forms or something knew about this. Okay, so all right, so these are the answers to, these are the kind of the starting point. And I wrote a celebrated analogy because what we're going to develop for the rest of this talk is the kind of continuation of these two columns where we're going to see that there's some kind of amazing parallels that will inform each other. Okay, so I'm going to ask you to do a couple more of these exercises. So I have in mind 2 more. So the first one I'd like to do is I'd like to think about what happens if we do calculus with these functions. Okay, so if we want to do calculus, the first thing we want to do is differential calculus. We want to think about functions in terms of their derivatives. Okay, so if you ask yourself, what are functions on a small disk? If you're a geometer, you already know these answers. This is kind of something we all learn in calculus, that functions on a disk are Taylor series. So that's what you get if you take a function, let's say on the line, and you restrict it to a small disk, you can expand it in this form. And if you, for example, allow your function to have just a pole at a point, so not be defined at that single point, but then be defined elsewhere, you'll find Laurent series. Okay, so the reason that a mathematician might like Laurent series better than Taylor series is because it's a field. So the first one's a ring, but the latter one's a field, and that connects with lots of other mathematics. Okay, so I hope everyone will recognize the answers that one finds in number theory. So if you're standing on, Ulam's spiral, or spec z, and you ask yourself, what are functions very close to the prime p? What you're asked to do is you're asked to complete the integers with respect to p, and you find the p-adic integers. Okay, so you end up writing power series in the variable p. And likewise, if you decide to allow poles, you'll get the p-adic numbers. Okay, so these fit into a single subject in algebra, study of local fields, and so there's lots and lots of results that don't really care which side of the divide you're on. Okay, but I'd like to point out a kind of very key property that make these two columns now radically different. Okay, and this is going to be one of the kind of motivating ideas. In this talk. So the key difference between these two is that if you're a geometer, all points look the same. Okay, so if you're standing on the complex line and you look at 0 or 1 or I, they're all related by translations. And if you look at functions on a small disk near any of these points, the functions are the same. Okay? But on the other hand, if you're standing on spec z, okay, so if you're standing on the number theorist's line and you look at 2 different points, they're really very, very different. Okay? So the primes 2 and 3 really have different behaviors. Okay? There are lots of theorems in mathematics that are true for 5, but not true for 2. Okay? So these fields are not the same. They're residue fields. I mean, Z mod P is a very different field for different primes. And so a number theorist has to deal with the fact that there's not this kind of evident translational symmetry that we have in geometry. Okay? So geometry has this beautiful fact that 2 points can be related to each other, but number theory, until recent times, doesn't have this, this property. Okay, so I'd like to now ask you to play this game one more time, and then I'll kind of continue on. I have my. Some people have nightmares about like forgetting to wear pants, so I don't give many slide talks. So I have this nightmare about running out of slides, which maybe will be fine because the schedule got pushed back. It rarely happens. I know everyone has. You prepare a linear algebra lecture, and you say, "Oh my gosh, I'm going to run out of material." Okay, so we'll see. Maybe anyway.
I may have to come and pull you on.
No, I'll be done before that happens, I hope. Okay, so I'm going to play this game one more time. I'm going to ask you to think about what is a curve in each column. Okay, so if you're bored with this game, either tune out or answer the question before I get there. So I'm going to give you a kind of a hint. So we know what a line is. Okay, so a line on each side is either a line as we traditionally know it or something we're calling spec z. So what should a curve be? So a curve should be something that's just finite over a line. If we've already decided that we know what a line is, then a curve should just be something that, say, maps to a line and has finite fibers. Okay? So it shouldn't have bigger dimension, it shouldn't be smaller dimensional, so it should be the same dimension, and one way to figure this out is to just ask that it map to the line and be a finite cover. So I couldn't find couldn't pilfer a nice picture, so somehow this picture seems to have some, the line seems to be a figure 8, but in any case you should picture as the downstairs space is like a line, and the upstairs space is some interesting cover of the line. Okay, so, okay. So, yeah, and there's a small, I realize there's kind of somewhat of a typo on this slide I'll comment on. So, okay, so in geometry, what we'll take is a Riemann surface, okay? So what is a Riemann surface? So it's a complex manifold of dimension 1, but one way you can think about it, and one way classical Riemann and others thought about when the notion was first being introduced was they would think of something that mapped to the complex plane with finite fibers. So they would think of some kind of differential equation, some ODE, say, on the complex line, and then you'd look at the sheets of solutions of this ODE, and you'd get something that covers it. Okay, so in geometry, we're going to all agree that a curve is going to simply be a Riemann surface. We may or may not care that it has a function on it, in other words, a map to the complex line, but that's going to be what a Riemann surface is. And now, I wrote the symmetries of the map is the fundamental group. That's not really true. What should be written is that the symmetries of such things living over sigma is the fundamental group, but somehow there was some mental disconnect when I was preparing the slide. So the fundamental group is the right mathematical object that governs these kinds of covers. Okay? So if you imagine that what you're interested in are curves, then the thing that governs curves is this kind of object, a fundamental group. Question? Okay, and in number theory, an analogous object is a number field. Okay, so we can look at an embedding of the rational numbers into a finite extension. And again, that side of the slide has the same kind of gap in that we shouldn't think of the symmetries of that embedding as being the Galois group, but the Galois group is the symmetries of F into its universal cover. So sigma might have a universal Riemann surface living over it, and similarly F might be inside an algebraically closed field, and the Galois group is the symmetry group that governs. Okay, so there we arrive at the mathematical formalism of global fields, and there are many, many theorems that work in parallel here. Okay, so we're done with those exercises, so now we're going to move on and see some really exciting developments of this kind of parallelism. Okay? So I hope I've convinced you. I mean, if you're a mathematician, which many of you are, then I'm probably boring you because I think these analogies are well known, but in any case, it's kind of an incredibly fruitful parallel. Okay, so let me just remind you of some amazing parallels that one can find in celebrated mathematics. So much of 20th century algebraic geometry was devoted to some conjectures of Weil that show that there's a deep relationship between these two columns when one just studies geometry over a point. Okay, so let me just try to remind you or invite you to learn about this by considering that just a very, very basic example of this number. So you take your prime and you add up 1 plus p squared and so on up to p plus n. Now if you're in geometry and you see that, so if you cover the right-hand side and you see it, you'll immediately recognize what that is. Okay, so that's the Poincare polynomial that encodes the Betti numbers of projective space. So projective space is a complex manifold of dimension n. Okay, so the Riemann sphere is the first example. It's a complex manifold of dimension n, and you can count, roughly speaking, the number of cells you need to build it up. And this generating series encodes the fact that you need one cell in each even degree. Okay, so somehow, I don't know, my Poincare polynomial is indexed by even degrees. Okay, but in number theory, there's an even kind of more elementary way to see the importance of this polynomial, which is you can count the number of lines inside n plus 1 copies of your field. Okay, so it might not be immediately obvious to you, but if you were to count lines the way I would count lines, you would count non-zero vectors. So you would count p to the n plus 1 minus 1 vectors, and then you divide out by rescaling, which is you would have p minus 1 rescalings. And that's, of course, the ratio of those two. Okay? So this is a kind of very well-known story, but in any case, a huge amount of 20th century algebraic geometry was devoted to generalizing this kind of parallel for algebraic varieties that are not as simple as this. Okay? So, so I want to emphasize that what I told you before could be thought of as a bit kind of, I don't know, fatuous, not sort of so serious, but at this point, this slide contains, I mean, I didn't tell you the theorems, but in any case, at this point, there's very, very deep mathematics extending this analogy. Okay, and a less well-known extension of this analogy, but one that I think is of kind of radical importance from where we go from here, is what happens when you compare algebra and geometry over a disk. Okay, so over a point, we are talking about comparing algebraic varieties, say, over the complex numbers or over a finite field. Now we're talking about comparing algebraic varieties over, on the one hand, say, Laurent series, and on the other hand, p-adic numbers. Okay? And there's an amazing story here, which is that model theory is a branch of logic I know very little about, but what it has been able to achieve is to show that if you just use the right vocabulary. I don't know a technical way to explain this. I'm not a logician, but if you use the right vocabulary, you use the right kinds of sentences, you can show purely for the fact that your logical systems are equivalent that certain formulas that you write down over the Laurent series are true if and only if they're true over the p-adic numbers. Okay? So it just means that the theories, in some logical sense, you have different symbols and different mathematical measurements that sense the difference, but if you ask the right questions, you can't tell them apart. Okay? And this was a kind of a 20th century development in logic, which got picked up in the 21st century, and I'll talk about this a little bit more, by people in harmonic analysis who are interested in this kind of game. Okay, so now sort of the story is going to become more vague because the ideas are going to be, in some sense, so grand that it's very difficult to convey them in any finite amount of time. So what is the Langlands program? So the Langlands program is a huge web of conjectures in number theory, conjectures and theorems, I should say. For example, last year's Breakthrough Prize winner Richard Taylor is someone who's proved amazing theorems in the Langlands program. And just to advertise to you that I'm not just telling you about my favorite pet theory, this is a kind of guiding principle behind Andrew Weil's proof of Fermat's theorem. So if you somehow, buy into mathematics, you'll buy into that, and then I hope buy into the Langlands program. Okay, so roughly speaking, what is the Langlands program about? Okay, so this is like, I tried to decide how to present what the Langlands program is on like one small slide, and I didn't want to be kind of completely dishonest, so I wanted to try to tell you some sense of what it is about, and so I tried. So let's see if it works. So to any Lie group G, okay, so to a continuous symmetry group G, there's always a dual group called the Langlands dual group, and a conjectural dictionary, meaning somehow that if you ask any question here, any reasonable question here, you can ask a parallel question there, and answers will match up. So a reasonable dictionary between functions on the locally symmetric space of principal bundles, so that's a kind of generalization for a group of the notion of a vector bundle, over an arithmetic curve given by a number field. Okay, so I don't want to try to parse that all, but I want you just to picture a number field as being something like a curve, and you're studying vector bundles on the number field. Okay, you study the moduli of those vector bundles. So that's some space that parameterizes vector bundles, and then you study harmonic analysis. In other words, you study functions on that moduli space. Okay, it's constructions on top of constructions. The right-hand side is very, very natural. I mean, if you took this to be the definition of what you're going to do in life, unless you had some mathematical background, it might sound a bit esoteric. But the right-hand side is very natural. You're going to look at the Galois group, the kind of symmetries of solutions to polynomial equations with coefficients in your field, and you're going to study representations of it. Okay? And so the amazing thing is that these two subjects are conjecturally and, well, by many, many theorems, deeply related. And it's a kind of vast generalization of things that when G is GL1, so when G is commutative, are kind of incredibly celebrated historic stories. So class field theory, Fourier theory. So anyway, this is a kind of amazing non-abelian generalization of like a huge, huge swath of mathematics. Okay. Now, what happened, as far as I understand the history, is that the Langlands program was formed. And then Drinfeld and Lamont as well decided to try to write down an analogy for it on the geometric side. Okay, so the Langlands program exists in this kind of number theory side, but you can make sense if you go back to this kind of these kind of paragraphs. You can make sense of everything that was in those paragraphs on the geometric side and try to see if there's going to be a parallel story in geometry. So this is kind of the first time that geometry deeply borrowed from number theory. So geometry sort of went into hock here because geometry, much of representation theory and algebraic geometry of curves is somehow related to this, and it was certainly inspired by number theory. Okay, so what we're going to first do is we're going to replace our number field, as we had before, with a curve, with a Riemann surface, and then we're going to end up studying the following conjectural dictionary. So to a Lie group G, there's the same dual group, and we're going to try to see what kind of relationship there is between now not harmonic analysis, but the very differential equations of harmonic analysis on the moduli of principal G bundles over a Riemann surface. So our curve now is really a Riemann surface. We still are studying principal G bundles, but now instead of studying the harmonic analysis, we're going to study the differential equations themselves. And that subtle difference, I wrote up an example, is the difference between studying an exponential function and studying the differential equation defining the exponential function. So the exponential function is somehow an object of analysis. The differential equation is an object that has a kind of more fundamental or basic existence in mathematics. Okay, and then instead of representations of the Galois group, we're going to study representations of the fundamental group. Okay? And so one reason to do this, outside of its intrinsic interest, is that here you have a chance to actually get somewhere. So every time you prove anything in the Langlands program, the original Langlands program, you do something worthy of worthy of some millions of dollars. And so you can ask, all right, can I find myself an easier context if, I just am interested in a salary? And the answer is, okay, there's maybe the geometric Langlands program. And so again, I don't want to overstay my welcome, but the tools here are much more robust. So if someone asks you to calculate the cohomology of, say, a complex manifold, there are many, many tools. There's Morse theory, there's cell decompositions, there's Hodge theory. Anyway, there's a huge number of tools, but I've asked you to count the points of an algebraic variety. It's a much less structured object. So in any case, it's a kind of very important, it's a kind of easier setting, but it's also very important because many, many structures, when you play this kind of a game, get new, you sort of have a new vision of them that you didn't have before. So for example, I could tell you I like the number n. And you could say, okay, what is n? I say, n's about 78. And you say, okay, so if by n you mean like I add up 2s, or I add up 1s, or I add up 30 and 48, what do you mean by 78? But if I told you 78 is the dimension of the vector space of functions on 78 points, then you would say, okay, that vector space has a canonical basis, the kind of characteristic functions of the point, and I understand 78 very well. It's 1 plus 1 plus 1 plus 1. Okay, so that is fatuous, but in any case, that underlying idea is kind of incredibly important in a lot of work in representation theory, the idea that when you work in this geometric context, there's a lot more structure. Okay, so once the geometric Langlands program was formulated, it looked just as hard as the original Langlands program. But then there was a kind of hint that it should be easier. And that's due to the key difference that I highlighted before. So in geometry, points of a Riemann surface are all roughly the same. Of course, that's not true. There's very deep theory about how points of a Riemann surface can be different. But in any case, you can move points around, and their local invariants are the same, whereas the primes of a number field are all different. And Beilenson and Drinfeld realized that to attack geometric langlands, it'd be very useful to exploit this added advantage of Riemann surfaces and apply ideas from conformal field theory. So the main idea is that the points of the Riemann surface can move around and collide, okay? Unlike the way that, say, 2 and 5 don't really move around and collide, okay? So points of a Riemann surface can move around, and they quickly realized that tools from physics, what are called vertex algebras, would be key ideas or key tools in this kind of game. And I wanted to, let's see if I have. So I mentioned that there's a fundamental physical principle here that's being used, even though Beilenson and Drinfeld were thinking like mathematicians, they of course were also somehow drawing deeply on physics. And that fundamental physical principle is that you want to understand complicated global outcomes by some simple local laws. So implicit in this story is, I just want to connect to some other breakthrough prize work. So last year, Jacob Lurie won a breakthrough prize, and he won it in part for some foundational work about this kind of algebra. So when you do algebra in the way most of us do algebra, you write across your sheet of paper things like 2 plus 3 times 7 minus 9, and you kind of work linearly, okay? But if you lived on a Riemann surface, you would do algebra like this. You might do 2 plus 3, but then you might multiply it by 7 coming in from the top. And you might divide by 3 coming in from the bottom, and so on. So there's algebra over a Riemann surface is an incredibly rich topic. It's a key idea in conformal field theory. And Beilenson and Drinfeld quickly proved a lot of things in the geometric Langlands program that look wildly outlandish to be able to prove in the traditional Langlands program. Okay, so yeah, I'm not going to, well, okay. I'll try to make your request, but we'll see. Okay, so I'd just like to shift perspectives, and I'm almost to my future predictions. So that's that's where it gets kind of interesting, I suppose. So okay, so I already hinted that the geometric Langlands theory now had some kind of very strong physical ideas in it, and people quickly recognized that what you were doing when you were playing this game was actually trying to match up physical boundary conditions for some quantum field theories on these two sides. And the only difference was that the symmetry constraints you imposed on the two sides had different names, okay? So on the left-hand side, what we've been previously thinking about as differential equations is what physicists would call A-branes. Okay, so I'm not going to try to explain this to you. But in any case, the physicists quickly say, okay, what you're doing is you're studying some things we call A-branes, which are some boundary conditions for some field theories. And on the algebraic geometry side, we're studying B-branes. And what's very enlightening about this is that it shows that what's going on here is a kind of duality. It's not a kind of dictionary where you have words and definitions. It's rather a duality where you have two types of mathematical objects that are, one is not kind of, one doesn't take precedence over the other. Okay, so I think in the name of time, I won't go through all of the comments that I was going to make here, except just to say that Maxime is in the audience, and this can be thought of as an instance of his homological mirror symmetry, which really says you should put a mirror between these two and see one side as simply a mirror of the other. So it's, again, a kind of much more symmetric relationship, which is very appealing if you're going to try to prove some theorems about both sides. Okay, so okay, great. So what have we done so far? So we introduced some analogies. There was some amazing inspired work in number theory, and then some developments in kind of a geometric analog. And then the physicists start to pile in some sense. So the physicists, will put 10 papers on the archive in the time that you brush your teeth. So once they got interested in this, it kind of really, some sort of exponential increase. So the physicists said, oh, well, I know something about this kind of duality. I know Maxwell's equations satisfy something called electromagnetic duality. So there's no real difference between, electric field and magnetic field. And, there's a kind of non-abelian version of that called 4D super-Yang-Mills theory. And we know that there's a duality for that, something called GNO. There's a GNO dual group. And anyway, there's a whole kind of dictionary that looks a lot like what those people in geometric Langlands are muttering about. And Atiyah already, according to Witten, in 1977 told Witten that this Langlands dual group they're talking about in number theory is really your dual group from four-dimensional super-Yang-Mills theory. And then Kapustin and Witten quickly said, so we should be able to understand this. So what is geometric Langlands? Okay, it's what we call Monton and Olive duality, which is part of S duality. That's something to do with six-dimensional quantum field theory. And this six-dimensional quantum field theory, we know it exists because there's something called M theory. And, well, M theory, we sort of are not sure it exists, but if it doesn't exist, we're in trouble. And so, great. So everything we understand because we understand M theory. Like if there's not M theory, then there's not this 6D theory, and there's not S duality, and there's not Monton and Olive duality, so there's not geometric Langlands. So we're happy with geometric Langlands because if it's not true, we've got really big problems. So of course you could ask, where are you going to go from here? And okay, I'm not sure. Maybe there are physicists in the audience who could tell us where we're going to go from here. But in any case, this is sort of where the subject stood until very recently. So I'd like to now take the last couple of minutes and try to play fortune teller. So I'd like to try to make some guesses, I hope educated guesses, about where this subject is going, and in some sense to explain to you what I think is very exciting, which is that geometry is now influencing number theory, okay, which is something that we hadn't seen to any great extent in this subject. Okay, so let me tell you about something that recently happened. So the tide has already turned in some sense, so we're just riding the wave at this point. But in any case, one of the most celebrated conjectures in the Langlands program was something called the fundamental lemma. That's Bob Langlands, and he said in 1979, it's a precise and purely combinatorial statement. Okay, so it's a very concrete statement, but impossible to prove. Okay, and then recently, Ngo Bao Cho gave a proof. He won the Fields Medal, essentially for the proof. And his proof follows this kind of dictionary that I've been laying out. So he studies this Hitchin system, which is really an object of physics, and then translates back to number theory. So without geometry, somehow there wouldn't be this proof. Okay, so it's possible that we will find proofs in the future that don't use geometry, but as of now, we need geometry to prove this. And I love this, ranked 7th. You can go Google this list, and you can find that it ranks 7th. And in fact, if you look on the list, teleportation was actually 8th. So, someone teleported a particle across, I think between two sides of a campus, and that was 8th. Okay, so anyway, so this was significant. This is, this is an important thing that was really influenced by geometry. And now let me just spend the last couple of slides telling you what I might predict or already see. I mean, not like I have any great vision, but I think the writing's on the wall. Okay, so what's the first thing? So the first thing is Peter Schulze. So Peter Schulze here in Berkeley last year gave a Chancellor's Professor course in which he introduced his notion of diamonds. I'm not going to tell you at all about what diamonds are, but he gave a first solution to this kind of question of how to collide two copies of the prime P. Okay, so if I think of 2 points on a Riemann surface, I can think of them kind of wiggling apart and colliding, and that's very important. That's how we take derivatives and so on. So Schulze invented a way to collide two primes. And in some sense, he solved the following fundamental question. If primes form a curve, what is a surface, right? If we need 2 points to be moving around, we need to think about a surface, right? The 2 points are like coordinates on a surface. Okay, so Euclid tells us what a surface is, so we're kind of happy, or maybe not, I don't know. Okay, so it's not a 3-space, that's essentially Euclid's definition. But Schulze tells us that there's a new notion of perfectoid spaces which allow you to talk about things like surfaces in this context and to actually produce mathematics that people up to now had only dreamed about. They dreamed about things like the field of one element and so on. But in any case, this is an amazing breakthrough, which, okay, that's just my speculation at the end, that in 50 years, when we have a graduate course, we'll have like, I don't know, it won't be Hartshorne's book, I suppose, but it'll be someone's book on perfectoid spaces rather than schemes. I don't know. So, okay. Now, the last slide I'd like to talk about is another exciting development in this direction, which is Laurent Fargue's recent conjecture about the classification of representations of p-adic groups, so what we call the local Langlands correspondence. And he recognized and conjectured that you can formulate this as a geometric Langlands correspondence on a curve, okay, on an arithmetic curve. So in other words, the tools of the geometric Langlands program actually can be specifically applied to a kind of arithmetic curve. So, okay, at the end of my rope or talk, but I think this is going to be one of the really exciting directions because it both will bring new tools and also further kind of bring these two fields together. So I just want to make, all right, so so this is a kind of a blatant advertisement for my own work, just the last slide. So I'll just mention a concrete instance of this paradigm that I didn't know what I was doing, but some years ago, David Ben-Zvi and I realized that you could study representations of real groups as a kind of geometric Langlands correspondence on unorientable surface RP2, essentially because its Galois group was, its fundamental group was the Galois group. So you can actually, already there was kind of some hint of this Farg picture, but only in a kind of very toy example. But I advertise it for those who might want to learn more about this. There's a kind of much more concrete version and has beautiful parallels. Okay, thanks very much.